Hello, good evening everyone, and welcome to the week 9 session of the course of Principles of Signals and Systems. So this is a tutorial for the week 9 content, and the content that was covered for this week was some more examples of the Fourier transform for continuous time signals, and followed by we had some examples or some discussion related to sampling of continuous time signals, and also we had after that an introduction to discrete time Fourier series. Okay, so now what we'll do is we'll start with a recap for this week's content. So the first thing that was covered in this week was the ideal low pass filter and its frequency response. So basically an ideal low pass filter looks something like this. Yeah. So it looks something like this. So it is non-zero for a particular band of frequencies. Let's say from minus omega c to omega c, it takes value as 1. So basically it passes to lower values of frequency, and that's why this is known as a low pass filter. Okay, the next thing that was covered was the rise time. The rise time for a simple RC circuit. Simple RC circuit, which is basically crude way or very basic low pass filter. So it is basically a circuit where R and C, that is resistor and capacitor, are connected in series, and the output is taken across your capacitor. So basically, and the rise time is given as the time which is required. So this rise time, this concept of rise time, let me define it properly. So this rise time is basically time needed or time required for the output to increase or rise from 10% to 90% of its maximum value. Okay, and this T rise for this RC circuit was obtained as 2.1972 RC, which is equal to 0.35 upon omega 3 dB, I'm sorry, not omega 3 dB, F3 dB. Okay, and after that, sampling of continuous time signals was discussed, and this Nyquist sampling theorem was discussed. So what it says is to reconstruct. So for any band limited signal, if we want to reconstruct it back after sampling, if we want to reconstruct back the continuous time signal, so the sampling frequency omega s should be at least equal to the maximum frequency which is available in the signal. So this is a Nyquist sampling theorem. So let us look at this theorem in a bit detail. So let's say I have a time domain signal which looks something like this. And let's say its Fourier transform is something like this, and it is band limited from minus omega m to omega m. Okay. Now, in order to obtain the samples of this signal xt, what we'll do is we'll consider a train of impulse such that the impulse is located at every integer multiple of ts, and this ts is basically known as, this ts is equal to sampling duration. Okay, so this ts is sampling duration, and when we multiply this signal with this train of impulse, we get the sampled version of the signal, which is something like this. So basically every impulse will be taking the value corresponding to the signal value of at that particular impulse location. and that's how we obtain the samples. Now this train of impulse has its Fourier transform as again one train of impulse which is located at the integer multiple of sampling frequency, angular sampling frequency. And if I'm having multiplication in time domain, I'll be having convolution in frequency domain. So if that is the case, then if I convolve x of omega with delta ts of omega and scale it, so in that situation I'll get replicas of this x of omega at every integer multiple of omega s, which is something like this. Now the diagram which is given here, so this diagram which is given here basically indicates the perfect Nyquist condition, like the Nyquist theorem is satisfied basically here. So basically here this omega m is smaller than or equal to omega s minus omega m. In this situation there is no overlap, which means that this omega s, that is sampling frequency, is greater than or equal to twice of omega m. Here there is no overlap. But suppose we have an opposite condition, which is something like this. So if I have a condition where this omega m is greater than omega s minus omega m, which means that this omega s sampling frequency is less than twice of omega m, then in that situation I'll be having an overlap between the adjacent replicas, and such a situation is known as aliasing. So this overlapping is aliasing, and this distorts the signal completely. And what is the result of this distortion? What is the result of this replicas or overlapping? Is we can't reconstruct back the original signal. So if I have this original signal, which is something like this, and if I pass it through a low pass signal such that this low pass filter is something like this. Okay, then in that situation I can regain back the original signals Fourier transform, which looks something like this. But if I have a situation here, and if I pass it through a low pass filter, which will be looking something like this, then obviously I won't be able to regain back the original Fourier transform, which means that I won't be able to reconstruct back the original signal. But if I am able to reconstruct back the original signal when this Nyquist theorem is satisfied, then I'll get an interpolation using sinc functions, which is something like this. I hope this part is clear to everyone. So basically, in order to reconstruct back or regain back the original signal, what we need to make sure is the sampling frequency is at least equal to twice the maximum frequency. Okay. Okay. After discussing sampling, the next part that was covered was discrete time Fourier series. So basically what it says is, suppose I have a discrete time signal x of n, and let's say this x of n is periodic. This is periodic with period n naught, which means that its fundamental angular frequency is equal to 2 pi by n naught, which is equal to omega naught. Then this periodic signal x of n can be written as summation k running from 0 to n naught minus 1 ck into e power j k omega naught n, and the ck's are basically obtained as summation n equal to 0 to n naught minus 1, or basically in any interval. So this I can also represent as n in any interval n naught with a scaling of 1 by n naught xn into e power minus j k omega naught n. Okay, so this is known as the discrete time Fourier series. Now the other things that are related to this Fourier series are basically, the first one is convergence. So discrete time Fourier series converge every time because this summation is a finite summation. So it is going to converge. The next thing that we have here is periodicity. So the CKs are periodic with period n naught. Next thing is the duality concept. So what we have is this ck, if it is in time domain, so its Fourier series coefficients will be x n naught into minus n. And the last one is the Parseval's relation. So it says that 1 by n naught, n running from 0 to n naught minus 1 magnitude x n square is equal to summation k running from 0 to n naught minus 1 magnitude of ck square. So this is the Parseval's relation. So this is all about the content that was covered in the week 9. So now let us go ahead and look at some examples related to these signals, these concepts. So let us look at the very first question. So what does it say? We need to find the cutoff frequency. So we need to find the cutoff frequency of an ideal low pass filter such that it passes exactly k% of the energy contained in this signal. Okay. So first of all, let us find the energy of this signal xt. So energy of xt, let's say it is given by E, is equal to integral minus infinity to infinity magnitude xt square dt. Okay. Now this is equal to integral from 0 to infinity e power minus at square dt, which I can write as 0 to infinity e power minus at, e power minus 2at dt. This is equal to e power minus 2at upon minus 2a from 0 to infinity, which is equal to 1 over 2a. Okay. Therefore, if I consider k% of E, then this comes out to be k by 100 into 1 by 2a, which is equal to k times 200a. Now what we need to find is, we need to find the cutoff frequency omega c. So what does it mean? So basically this is my low pass filter. Which is something like this, let's say with magnitude 1. This is minus omega c, and need to find the value of this omega c. Okay. So for that we'll use the concept of energy spectral density. So this ESD, or energy spectral density, is basically magnitude of x of omega square. And energy in this region, let's say energy hat, is basically 1 over 2 pi integral minus omega c to omega c magnitude of x of omega square d omega. Okay. So for that, let us first find out what is x of omega. So this x of omega is a Fourier transform of this exponential, which is a standard function, and we have found it multiple times. So basically it is equal to 1 upon j omega plus a, which implies that magnitude of x of omega square is equal to 1 upon omega square plus a square. I hope this part is fine with everyone. So now what we'll do is, we'll consider E hat, which is equal to 1 upon 2 pi integral minus omega c to omega c 1 upon omega square plus a square d omega. So this I can also write as 1 upon 2 pi into 2 times integral 0 to omega c, since it is an even function, 1 upon omega square plus a square d omega. This I can write as 1 by pi a tan inverse of omega by a. Okay, and this E hat should be equal to this k% of E, which is k upon 200a. So it is equal to k upon 200 A. Okay, so therefore this is basically omega c. So what I have is this A gets cancelled, so this tan inverse of omega c by A is equal to k pi upon 200, which means that omega c is equal to A times tan of k pi by 200. Okay, in the class the example that was considered was basically equal to when k is equal to 50. So if my k is equal to 50, that is it passes half of the energy, then omega c will be equal to A times tan of pi by 4, which is equal to A, and this is in radians per second. I hope this part is clear to everyone. Okay. If that is the case, then let us move ahead with the next example. Okay, so now what we'll do is we'll consider this example. Where we need to find the rise time. Okay, we need to find the rise time of the series RC circuit. So the circuit that we are having is something like this. We have this resistor R. We have this capacitor, which is C. The input is the input is given here, and the output is taken across the capacitor. That is, output is basically the voltage across this capacitor. Okay, so now we have been given three cases. Okay, so three conditions are given here of R and C, and we have seen that this T rise is equal to 2.1972 RC, and this is in seconds. So let us consider the first example. So here R is equal to 1 kilo ohm and C is equal to 1 microfarad. So T rise is equal to 2.1972 multiplied by 1 kilo ohm, that is 10 raised to 3, into 1 microfarad, that is 10 raised to minus 6. So this comes out to be 2.1972 into 10 raised to minus 3, which is equal to 2.1972 milliseconds. Okay, now let us look at the second example. So what we have is T rise is equal to 2.1972 multiplied by 10 kilo ohm, so that is 10 into 10 raised to 3 ohm, multiplied by 1 microfarad, that is 10 raised to minus 6 farad. So again this comes out to be 21.972 into 10 raised to minus 3, so this comes out to be 21.972 milliseconds. Okay, now let us look at the third part of this question. So here what we have is T rise is equal to 2.1972 into 1 kilo ohm, that is 10 raised to 3, multiplied by 1 nanofarad, that is 10 raised to minus 9 farad, which comes out to be 2.1972 into 10 raised to minus 6, which is equal to 2.1972 microseconds. Okay, now let us try to understand this with the help of graph. Now note that the output, this y of t, is basically equal to 1 minus e power minus t by rc into ut. Okay, now let's say this is my yt, this is my t axis, and let's say this is 1. Okay, so this is 1, this is y of t axis, and this is the 1 is the maximum value of output that it can get. So if I consider the first case, then let's say it goes this output is going something like this. Okay, so this is for the first case, and we know that, let's say this one is 0.9 and this one is 0.1, so mark it something like this. Yeah, so let's say this is 0.9 and this is 0.1, and let me mark these lines. dark, something like this. Yeah. Okay. Then this duration, this duration is basically equal to the time which is required to for it to go from point 1 to point 9, and this we have obtained as 2.1972 milliseconds. Okay, now if we look at the second case, then it will start from here. So it will start from here and then it will go something like this, and it will slowly go to 1, something like this. Yeah. Okay. Now if we observe carefully this part, okay, this one is basically 21.972 milliseconds. Okay, now if we look at the third case, it rises very quickly, like it rises in 2.1972 microseconds. So basically it will go something like this. Okay, so it is basically this region. This part. This is basically 2.1972 microseconds. So what we observe is, smaller the value of t rise, or smaller the value of r into c, faster it will reach to its maximum value. So smaller the value of time constant, which is equal to rc, faster it will reach to its maximum value. I hope this is clear from this example. If it is not, please let me know. I'll put more light on this. If not, then let us go ahead for the next question. So now we'll look at a few questions which are basically related to Nyquist sampling rate. Okay. So now let us start looking at these questions. So what we have been given is, we have been given a signal xt with Nyquist rate omega naught. So what does this mean? Let's be very specific, that is xt is band limited, and let's say its maximum frequency is omega m. Okay, so if this xt is band limited and its maximum frequency is omega m, which means that this omega naught is equal to 2 times omega m. This is the information that we are extracting from the very first sentence of the question which we have been given. Now let us get to the next part. We need to find the Nyquist rates for the following signals. So what all signals do we have? So the first signal that we have is xt plus xt minus 1. So let's say this is x tilde t, which is equal to xt plus x of t minus 1. And we can't do anything, or we can't say anything by just looking at the time domain representation. So let's go to a convenient tool, which is the Fourier transform. So let's say x tilde omega is its Fourier transform. So it is equal to x of omega plus e power minus j omega, which is from the time shift property of Fourier transform, into x of omega. So this I can write as x of omega, and also I can take out e power minus j omega by 2 outside, or let me do it step by step. So this is equal to x of omega into 1 plus e power minus j omega. So to make more sense of this, what I'll do is I'll take out common e power minus j omega by 2. So x of omega into e power minus j omega by 2. Inside the bracket it is e power j omega by 2 plus e power minus j omega by 2. This is equal to x of omega into e power minus j omega by 2 into twice cos of omega by 2. So if I multiply and divide it by 2, so this factor here is basically equal to cos of omega by 2. Now let us try to plot this. So instead of this, I will just plot magnitude of x of omega, which is equal to magnitude of x of omega, which is twice of this, into cos of omega by 2. Okay, now let us try to plot it. So let's say this is minus omega m, this is omega m, this is omega, and let's say this x of omega, mod of x of omega is something like this. Okay, and another thing that we are having is this cos of omega by 2, so let's say this is scaled by a factor 2 as well. Okay, and what we have is cos of omega by 2, so it's something like this. And so on, similarly like this. Now make a note of this fact that this goes from minus infinity to infinity for omega belonging to this range, and this is only when omega belonging to minus omega m to omega m. I hope this part is fine. So if I multiply these two things, the resultant, this x tilde of omega, will be non-zero only when omega belongs to minus omega m to omega m, which means that maximum frequency is equal to omega m, which means that Nyquist rate is equal to 2 times omega m, which is equal to omega. Okay, I hope this part is clear to everyone. If it is, then let us go ahead and solve the next part of the same question. So what we have been given here is, now we have this x tilde t is equal to x square t. Now if I take the Fourier transform of it, so let's say this is x tilde of omega, it will be equal to 1 over 2 pi. So this is using the time multiplication property. So it will be 1 over 2 pi into x of omega convolved with x of omega. Now let us try to understand what happens to the frequency range when it is getting convolved. So what we are having is something like this. Let's say this is x of gamma, this is gamma, and it is something like this. And for convolution, I need to flip this again. So let's see, this is x of minus gamma. Okay, now this overlap, you need to check from where the overlap starts. So basically this is the case when omega equal to 0. Now the overlap starts when omega equal to minus 2 times omega m. This is omega m, this is also omega m with a minus sign. Okay, so if it is here, then I am having this somewhere here, so it will be something like this. Okay, so this is minus 2 omega m, this is minus omega m, and this is basically x of minus 2 omega m minus gamma. Okay, so overlap starts here. Similarly, the overlap ends when omega equal to 2 omega m. So that is x of 2 omega m minus gamma, which will look something like this. So basically this one is 2 omega m and this is equal to omega m. So overlap ends here. So from this what we can say is this x tilde of omega is non-zero only when this omega lies in the range of minus 2 omega m comma 2 omega m. Okay, then in this situation what we have is the maximum frequency in x tilde of t is 2 times omega m, which is equal to omega naught, which means that Nyquist rate is equal to 2 times omega naught. Okay, this is okay. Okay, fine. Let us look at the third part of this question. So here this x tilde t is equal to xt into cos of omega naught t. Okay, so we know that this xt has a Fourier transform x of omega, and this thing here has a Fourier transform of pi of delta omega minus omega naught into plus delta omega plus omega naught. Okay, and this x tilde omega is basically 1 over 2 pi x of omega convolved with x tilde of this factor here. So basically this x tilde omega is equal to this pi gets cancelled with this pi 1 over 1 over pi x of omega convolved with this delta with this simple set omega is basically x of omega minus omega naught plus x of omega plus omega naught. Now let us try to find where the maximum frequency of the signal lies. Okay, so yeah, let's say this is omega naught, this is omega naught by 2, which is equal to omega m minus omega naught by 2, this is minus omega naught. So basically the signal is something like this. Okay, which means that maximum frequency is equal to this, which is omega naught plus omega m, which is omega naught by 2. So maximum frequency is equal to omega naught plus omega naught by 2, which comes out to be 3 times omega naught by 2, which implies that Nyquist rate is equal to 3 times. Okay. Yeah. Okay, fine. Let us look at the next question then. So this question also has two parts. Now this sampling thing is an important thing. Basically this sampling is done because we can't store continuous time signals in our computers, and basically this sampling is very first step of what we call as analog to digital conversion. So once we had discretized the signal along time axis, then we go for quantization process. So for the complete process of conversion of analog signals to digital signals, the very first step is to convert a continuous time signal to a discrete time signal. and that process is known as sampling. And we saw in the initial discussion that consideration of the sampling frequency, or choosing a very proper sampling frequency, is very important. And if we don't do that, then we'll face what is known as aliasing, and we'll see the consequence of that in one of the upcoming example. But hence deciding a Nyquist rate, like if I'm having a, if I need to sample at the output of any system, then I should know the what is the maximum value of frequency that I can expect at the output, and accordingly I can design the sampling or the sampler at the output of my system. So these things play a very important role in designing of any communication or any signal processing systems. So that's why we are taking these basic operations and looking at how the sampling frequency changes if I do some operation with one signal or do operations with two signals. So what we have been given in this example is basically I have two signals. So I have x1 of t, and this has a sampling frequency or Nyquist sampling rate as omega 1, which means that maximum frequency omega m1 is equal to omega 1 by 2. Okay, and second thing is omega x2t has Nyquist sampling rate as omega 2, which means that omega m2 is equal to omega 2 by 2. Okay, I hope this till this point it's clear. Now what we need to find is, we have been given y1 of t, which is equal to x1t into x2t. So if I take its Fourier transform, then y1 of omega will be equal to x1 of omega into x2 of omega. Now let us try to understand, when I am multiplying these two things, what is important is which is the maximum frequency and which is the minimum frequency in both of these signals. So what we'll have is two cases. So the case 1 is omega 1 is greater than omega 2. If that is the case, then we have a situation something like this. So this is 0. Omega 1 is greater than omega 2. So first we'll have omega 2, then we'll have omega 1. Similarly, minus omega 2 and minus omega 1. So omega 1 is greater. So let's say we have a signal which is something like this and like this. So if I multiply these two signals, what I'll get is this y1 of omega will not be equal to 0 for omega belonging to minus omega 2 to omega 2. Okay. Similarly, if I have case 2, where this omega 2 is greater than omega 1, so we'll get exactly opposite thing. So let's say this is 0, this is omega 1, this is omega 2, this is minus omega 1, this is minus omega 2, and what we have is something like this. This is x1 of omega, and this is x2 of omega. And now again, this is the region, that is this y1 of omega is not equal to 0 for omega belonging to minus omega 1 to omega 2. So from these two cases, what do we observe is the maximum frequency of this y1 of omega. So let's say omega m y is maximum frequency of this y1 of omega is basically minimum of omega 1, omega m1, comma omega m2. So basically this will be omega 1 by 2 everywhere. Yeah. That is minimum of omega 1 by 2 comma omega 2 by 2. Okay, which means that Nyquist rate is equal to, let's say omega naught is equal to 2 times omega my, which is equal to 2 times minimum of omega 1 by 2 comma omega 2 by 2. I can take this 2 inside, so this will be equal to minimum of omega 1 comma omega 2. Is this okay? Any questions at this point? Okay. Let us look at the second part of this question. So what we have is y2t is equal to x1t into x2t. So again we are having multiplication in time domain. Okay, then in this situation what we are going to have is y2 of omega will be equal to 1 over 2 pi x1 of omega convolved with x2 of omega. Okay, then suppose we are having this situation. Okay, so this is 0 omega omega, this is x1 of omega, this is x2 of omega, and what I am having is this is x1 of omega, this is omega m1, this is minus of omega m1, and I have this something like this, this is omega m2, this is minus omega m2. Okay, then if I convolve this, then the minimum frequency in y2 will be equal to addition of these two, addition of the minimum two frequencies. So that will be equal to minus omega 1, omega m1 plus minus omega m2. So it will be equal to minus of omega m1 plus omega m2. Similarly, maximum frequency in y2t will be equal to addition of these two. Okay, so what we'll have is omega m1 plus omega m. Therefore, Nyquist rate will be equal to 2 times the maximum frequency, that is 2 times omega m1 plus omega m2, which is equal to 2 times omega m1 plus 2 times omega m2, which comes out to me omega 1 plus omega 2. So this is the Nyquist frequency that we'll need. Okay, this is the Nyquist frequency that we'll need in order to sample the multiplied version of x1t and x2t. Is it okay? Okay, fine. Let us look at the next question, which is the fifth question of today's session. And what it says is, let's say xt is equal to a for t in minus 10 to 10. So let us first draw this signal. Okay, so this is xt. It is non-zero for minus 10 to 10. Something like this. Yeah. So this is t. This is x of xt. And its magnitude is a. Okay. And x of omega is its continuous time Fourier transform. And we have seen in the class that this has a Fourier transform of 2a sine of 10 omega upon 10 omega. Omega. Okay. So this is the Fourier transform of this, which is equal to x of omega. Now what we need to find is, we need to find the sampling frequency of xt convolved with capital XT. So for that, let's consider xt is equal to 2a sine 10t upon t, and this will have Fourier transform using duality property as 2 pi of x of omega, x of minus omega, which will be equal to 2 pi x of omega. So this will be same thing, but it will be scaled by a factor of 2 pi. So this is omega, something like this here. This is minus 10, this is 10. So again I'll have minus 10, 10. Here something like this. And this will be 2 pi a. Okay. Now this this y of t is basically xt convolved with capital XT, which means that y of omega is equal to xt multiplied by capital X of omega multiplied by this factor, that is 2 pi omega. Now note that this x of omega is ranging for omega belonging to minus infinity to infinity, but this factor here is ranging only for omega in minus 10 to 10, which means that if I multiply these two signals, because since this x of this is x of omega, so if I multiply these two signals here, then since this x of omega is non-zero, is 0 outside minus 10 to 10, this y of omega is non-zero only for omega belonging to minus 10 to 10, which implies that maximum frequency omega m is equal to 10 radians per second, which means that Nyquist frequency, so this omega s is basically Nyquist rate, is equal to 20 radians per second. Is it okay? Okay, fine. If it is okay, then let us go ahead and look at the sixth question, and yeah, it is the last question which we'll do for which is based on sampling. So what it says is, I have been given a signal xt which is equal to cos 100 pi t plus cos 200 pi t plus cos 500 pi t and plus cos 1000 pi t, and this signal is sampled at a sampling frequency of omega s is equal to 600 pi. After sampling, it is passed through a low pass filter with cutoff frequency 700 pi, and let's say it is an ideal low pass filter. Okay, so now we need to determine which all frequencies are present in the resultant signal which we are obtaining after the low pass filtering operation. Okay, so for that what we'll do is, let us first find the Fourier transform of xt and sketch it. Okay, so let's say the Fourier transform of xt is x of omega. So this x of omega is basically pi times some impulses which are located at the respective frequencies. So for the first cos, it will be located at plus minus 100 pi. So it will be delta omega minus 100 pi plus delta omega plus 100 pi. Then for this second function, second cos, it will be located at plus minus 200 pi. So it is basically delta omega minus 200 pi plus delta omega plus 200 pi plus minus 500 pi, so it is basically delta omega minus 500 pi plus delta omega plus 500 pi. Similarly, for this 1000 pi factor, I'll have an impulse delta omega minus 1000 pi plus delta omega plus 1000 pi. I hope till this point it's clear. Okay. So now let us try to sketch this signal. Okay. So this is what we have. Let's say this is this is 2000 pi. This is 1000 pi. This is minus 2000 pi. This is 1000 pi. 500, 500, 150. Yeah. 200, 100, 200, 300, 400, 500, 600, 700, 800, 900, 100, 1100, 1200, 1300, 1400, 1500, 1600, 1700, 1800, 1900. Similarly, okay, so let me just write these properly. So this is 0, this is 100. For simplicity, I am not writing the factor pi, so note that this is basically pi times omega. So for easy, I am just removing the pi and it is pi times omega. Okay, yeah, so this is 100, then 200, 300, 400, 500, 600, 700, 800, 900, 1000, 1100, 1200, 1300, 1400, 1500, 1600, 1700, 1800 and 1900. Similarly, on negative side, I'll have minus 100, minus 200, minus 300, minus 400, minus 500, minus 600, 700, minus 800, minus 900, minus 1100, minus 1200, 1300, minus 1400, minus 1500, minus 1600, minus 1700, minus 1800 and minus 1900. This is minus 2000. Okay, everything is basically scaled by a factor of pi. Okay, so where all do we have these impulses? So we have impulses at plus minus 100, something like this. Okay, then we have it at plus minus 200. Then we have it at plus minus 500. And at plus minus 1000. Okay, so this is basically x of omega. Okay, now what we have been given is this x of omega, this xt is sampled this xt is sampled with a sampling frequency. This xt is sampled with a sampling frequency as 600 pi. Okay, so when we are sampling with a sampling frequency, so with 600 pi, so what does this mean? That we'll have replicas of x of omega at integer multiple of sampling frequency, which is basically equal to 600 pi. Is it okay? So now let us consider the first integer multiple, that is at 600 pi. So initially this was my x of omega. This will be there. This will be there because it is for integer 0. So along with that, let's say this is 600 pi, the first angular frequency that I am having. So if we observe here, if this is my reference, then from reference I have an impulse at plus and minus 100. So I will have an impulse here and superposition of impulse here. Similarly, I have it at plus minus 200. So it will be 600 plus 200, that is 800 pi, and 600 minus 200, so that is 400 pi, which is somewhere here. Also, I have it at plus minus 500. So 600 plus 500, it is 1100. So it will be here. Also, 600 minus 500 is 100. So it will be here. Okay. One more thing. It is at 1000 plus minus 1000 as well. So 600 plus 1000. So if I do 600 plus 1000, it is basically 1600, which is located here. And 600 minus 1000 is basically minus 400, means it is located here. Similarly, I have the case when the integer is minus 1. So this minus 600 is now my reference. So if I do that, I'll have replicas at plus minus 100. So it will be at minus 500 pi and minus 700 pi, plus minus 200 pi. So it will be at minus 400 and minus 800. Exactly symmetric we'll get. Then if I do plus minus 500, then one will be at minus 1100 and another will be at minus 100. I'm sorry, minus 600 minus 500. Oh, sorry, minus 600 plus 500. So it will be at 100 somewhere here. And plus minus 1000. So one will be at 400 here. And one will be at minus 1600, which is here. Okay. Similarly, what I'll have is, let's consider when my k is equal to 2. Okay, so suppose now my k, let me use some totally different color. Yeah, this one. So now what I'm having is my k is equal to 2, which means that I'll have the reference as minus 1200. So again, plus minus 100, I'll have one impulse. Similarly, at plus minus 200, I'll have an impulse. Then I'll have an impulse at plus minus 500. So 1200 plus 500 is 1700, that is here. And 1200 minus 500 is 700, so it will be here. Similarly, at plus minus 1000 I'll have. So one I'll have at 200. And 1200 plus 1000 is basically 2200, so it will be somewhere here. Okay. Similarly, what I have is at this location, that is minus 1200, which is here. So what I'll have is, let me use this color. Yeah, plus minus 100 I'll have impulses. Similarly, at plus minus 200 I'll have impulses. Plus minus 500 I'll have impulses. So 1200, so it will be at minus 700 and 1700. Then at plus minus 1000 I'll have it. So minus 1200 plus 1000, so it is 200, and minus 1200 plus minus 1200 minus 1000, so it will be at minus 2200 somewhere here. Same thing has to be repeated over again and again for all the integer values of frequencies. Now apart from that, what thing we have been given is this fact here, that is after this sampling process we are passing it through a low pass frequency, low pass filter, and that filter's cutoff frequency is minus 700 to 700. So how does it look? So it looks something like this. So let's say this is okay. So it is something like this. Yeah. So this is my low pass filter, and if I consider it and if I just focus on the positive frequency, so the frequencies present are 100, 100 pi, 200 pi, 400 pi, and 400 pi, 500 pi, and 700 pi. So these are the frequencies that are present. Now if we would have sampled it properly, then what we were expecting is to have something like this. That is, we would be expecting frequencies only to be present at 100 pi, 200 pi, and 300 pi. But due to improper sampling frequency, I am getting additional frequency components. So I am getting additional frequency components at 400 pi and 700 pi, which are not present in the previous, in the original signal, but due to sampling with improper sampling frequency, or with a sampling frequency which is less than Nyquist rate here, which was 2000. So since it was less than the Nyquist sampling rate, I am getting overlapped version of my inputs, overlapped version, or aliasing or overlapping between the adjacent components, adjacent replicas, and that's why it is very necessary that we take or choose an appropriate sampling frequency. I think this example demonstrates it very nicely, like why actually the sampling frequency is needed, a proper sampling frequency is needed. Okay, so if this question is clear, so let me go ahead with the next questions of this session. So now I'll be focusing on the new concept that was introduced in this week, or rather I won't say it as a new concept, but an extension to the Fourier series concept which was introduced previously for the discrete time signal case. So let us try to solve few questions based on those things. So let us look at the very first example, and it says that we need to find the Fourier series coefficients for this particular signal. So let's say this is xn, this is my n axis. So this is 0, 1, 2, 3, 4, 5, and we can observe here that the signal starts repeating. So the signal starts repeating from 6. Okay, which means that it repeats after every 6th instant. And if that is the case, then we can say that this xn is a periodic signal with period n naught is equal to 6. Okay, which means that my angular frequency, or the fundamental angular frequency, is equal to 2 pi by n naught, which is equal to 2 pi by 6, which is equal to pi by 3. Okay, so this is what we have here. So let us try to find out the Fourier series coefficients. So this is equal to 1 over n naught, where n naught is 6, summation k running from 0 to n naught minus 1, that is 6 minus 1, which is 5, xn into e power minus jk omega naught n. So this I can write as 1 by 6 inside the bracket x of 0 into e power minus jk omega 0. So this reduces to 1 plus x1 into e power minus jk omega naught is pi by 3 plus x2 into e power minus jk 2 pi by 3. And notice that this factor here from x3 to x5 is 0, so I can simply ignore those terms. So it's not needed to write those terms, and we know that this x0, x1 and x2 are all 1, so I can simply replace it. So let's say 1 by 6, 1 plus e power minus jk pi by 3 plus e power minus jk 2 pi by 3. This what I can do is 1 by 6, 1 plus I can take out e power minus j pi by 2 common. So here what we have is e power jk pi by 6 plus e power minus jk pi by 6. Now this, if I divide and multiply by a factor of 2, then this factor here is basically cos of pi by 6 into k. Now let us evaluate this factor here. So what we are having is, with a k here, yeah, e power minus j k pi by 2, I can write as e power minus j pi by 2 whole power k, which is equal to cos pi by 2 minus j times sin pi by 2 whole to the power k. Cos pi by 2 is 0 and sin pi by 2 is 1, so this is basically minus j to the power k. So the ck is equal to 1 by 6 inside the bracket 1 plus 2 times minus j to the power k cos of pi by 6 into k, and the DC component C0 is obtained as 1 by 6 inside the bracket 1 plus 2, which is equal to 3 by 6, which is equal to 1 by 2. So even if you find the average of these components, that is 1 plus 1 plus 1 whole divided by the period 6, that will be again equal to 3 by 6, which is equal to 1 by 2. I hope this this part is clear to everyone. If it is, then let us go ahead and look at the next example. Okay, so we have another example here. So this is my xn and this is my n. Now if you observe carefully, this factor here is basically x0, this is x1, this is x2, this is x3, and the signal starts repeating here. Again repeats here, which means that the x of n repeats itself after every fourth instance. So look here, it is basically repeating from fourth instance. So basically this means that this xn is periodic with period and not equal to 4, and therefore the fundamental angle of frequency is omega naught omega naught is equal to 2 pi by n naught, which is equal to 2 pi by 4, which comes out to be pi by 2. Okay, now let us try to find out the Fourier series coefficients. So what we have is ck is equal to 1 over n naught, which is 1 by 4, summation n running from 0 to n naught minus 1, which is 4 minus 1, which is equal to 3, summation of xn into e power minus jk omega naught is pi by 2 into n. Okay, now let us simplify this. So we have 1 by 4. Inside the bracket we have x0 into 1 plus x1 into e power minus jk pi by 2 plus x2 into e power minus jk pi plus x3 into e power minus jk 3 pi by 2. Okay, so this I can write as 1 by 4. X0 is 3. See, this x0 is 3 plus this x1 takes the value as 2 plus 2 into e power minus jk pi by 2, which we have found out as minus j power k. So I'll just replace it as minus j to the power k plus x2 takes the value as 1. And now let us try to find out what exactly is this e power minus jk pi by jk pi. So this is e power minus jk pi, which is equal to e power minus j pi whole to the power k, which I can write as cos pi minus j times sin pi whole to the power k, which is equal to minus 1 to the power k. So this I can write as 1 into minus 1 to the power k. So this is minus 1 to the power k plus this x3 is 0. So what we have is ck is 1 by 4. Inside the bracket it is 3 plus minus j to the power k into 2 plus minus 1 to the power k. Okay. Now let us look at what is its DC component. So it is equal to 1 by 4 inside the bracket 3 plus 2 plus 1 plus all zeros. So it is equal to 6 by 4, which is equal to 3 by 2, which I can write as 1.5. I hope this part is clear to everyone. So this is the Fourier series coefficients. So these are the Fourier series coefficients for the considered signal. Okay. Yeah. If this is clear, then let us go ahead and look at the next example for the Fourier series coefficients. Okay. So now what we have been given is the signal xn is equal to e power n for all n from 0 to 3, and we need to calculate its Fourier series if it repeats itself after every fourth instant. So let us first try to draw. Let us first try to draw this signal. So let's say this is xn. This is xn axis. This is n. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So what we have is it is equal to e power 0, that is 1 here. Then it is e square. So basically it is equal to 1, then it is equal to e square. Sorry, e, then it is equal to e square, and then it is equal to e cube. So then it starts repeating itself from 4. Then it is equal to e square, e power 4, e 1 e, and so on. Okay, so this is what we are having. So it goes on continuously. So what we are having here is we can observe that this xn is periodic with period and not equal to 4, which means that omega naught is equal to 2 pi by 4, which is equal to pi by 2. So this is the information that we are having here. Therefore, now let us try to find the Fourier series coefficient. So the Ck is equal to 1 by n naught, which is 1 by 4 summation k running from 0 to 3 xn into e power minus jk omega naught is pi by 2 into n. So this I can write as 1 by 4 inside the bracket x0 into 1 plus x1 into e power minus jk pi by 2 plus x2 into e power minus jk pi plus x3 into e power minus jk 3 pi by 2. Okay, now this x0 is equal to 1. So what I have is this x0 is equal to 1. So I'll write it as 1 plus x1 is e power 1. So that is e into e power minus jk pi by 2. So we have found it as minus j power k plus x2 is e square, and it is e power minus jk pi, which we obtained as minus 1 to the power k, plus x3 is e cube into e power minus jk pi by 3 jk 3 pi by 2. So let us write this as e power minus jk 3 pi by 2 as cos of 3 pi by 2 minus j times sine of 3 pi by 2 whole power k. Sine 3 pi by 2 is minus 1 and cos 3 pi by 2 is 0. So this is basically equal to j power k. So this is j to the power k. So what we are having is 1 by 4 inside the bracket 1 plus minus j to the power k into e plus minus 1 to the power k into e square plus j power k into e cube. Now if I go ahead and find the TC coefficient, then it is equal to C0 is equal to 1 by 4 inside the bracket 1 plus e square plus e cube. So this is basically my DC coefficient. So this is DC coefficient. And this is the Fourier series for the given signal. Is this okay? Okay. Then if this is fine, then let us go ahead and look at the next question. Okay, so let us look at this question. So what does it say? We have been given a signal xn, and this xn is equal to 1111 for, and let's say this starts from n equal to 0. This arrow basically indicates that it starts from n equal to 0. Okay, so this is what we have been given. First thing, this is my xn. Then what I have been said is I have a signal yn, which is convolution of xn with itself. These are the two informations that we have been given till this statement. Next thing is y1 of n. So basically it is not y1 of n, y1 of t, it is basically y1 of n is yn repeated after every 10th sample, and we need to calculate the Fourier series of y1 of n. Okay, so let us look at what all things we have been given step by step. So the first thing that we have been given is xn is equal to 1 1 1 1, and it is 0 otherwise. So how does it look? It looks something like this. This is n, this is xn axis, this is 0, so it is basically 1 1 1 1 at 0 1 2 3, and it is 0 otherwise. Okay, So this is the xn that has been given to us. The next thing that we have been given is y of n is basically equal to convolution of xn with itself. Is it okay? Yeah. And the third thing that is given is this y1 of n is basically this xn repeated at every integer multiple of 10 from L running from minus infinity to infinity. Okay, so now we need to find the Fourier series coefficients of this y1n. So this can be found in 3 steps. So step 1, find yn which is equal to xn convolved with itself. Step 2, find y1 of n, its period and its angular frequency. And step 3, find Fourier series coefficients of y1 of n. Okay, so now let us try to solve this step by step. So let us start with step 1, finding yn is equal to xn convolved with itself, that is xn. So this I can write as summation k running from minus infinity to infinity xk into x of n minus k. Okay, so let me sketch it. So for convenience, let me just take this above so I have enough space. Let's say it's here. Yeah. Okay. Okay. So okay. So this is what I have. So let me first sketch xk. So it looks something like this. This is 0, 1, 2, 3. This is k axis. This is xk, and it is 0 otherwise. Okay. Now what I'll do is I'll first sketch what is x of minus k. So this is basically flipped version of xk, which is something like this, and it is 0 otherwise. And so on, this is k, and basically this is when n is equal to 0, which means that y of 0 will be equal to just 1 into 1. So this is 1, this is also 1, so it is just equal to 1 into 1, which is equal to 1. So this is n equal to 0, which implies that y of 0 is equal to 1 into 1, which is equal to 1. Okay, now let us consider, or let us look at x of 1 minus k, which means that n equal to 1. So how does it look? This went up. Yeah. Okay. So this means that we are just shifting it by a factor of 1 to the right. So it will look something like this. It is 0 otherwise. So this is when n is equal to 1, which means that y1 is equal to 1 into 1. So I am having two overlaps, one at here and another at here, plus 1 into 1, which is equal to 2. Okay, now I'll again shift it by one factor, 1 unit. So it's something like this. It is 0 otherwise. So this is equal to x of 2 minus k, and this is basically n equal to 2, which means that y2 is equal to, I am now having three overlaps, that is at this location, this and this. So this is equal to 1 into 1 plus 1 into 1 plus 1 into 1, which comes out to be 3. Okay, now next thing what I'll do is I'll again shift it by one factor since my overlap is still there. So it is something like this. It is 0 otherwise. So these all are k axis. So this is equal to x of 3 minus k. And now if you observe, there is a perfect overlap, that is that there is an entire overlap with this one and this one, this one and this one, this one and this one, which means that for n equal to 3, what I have is y of 3 is equal to 1 into 1 plus 1 into 1 plus 1 into 1 plus 1 into 1, which is equal to 4. Okay, now let me add another page and let's see, this is xk. Okay, so let's say this is xk. I'm just redrawing the stuff. So it is 1 for these 4 locations, that is 0 1 2 3, and it is 0 otherwise. Okay, and we have already found it till n equal to 3. So what we'll do is now we'll consider x of 4 minus k, that is k equal to n equal to 4. So we'll again shift this. We'll shift this by 1 unit towards right. So basically it will start from 1, 2, 3 and 4, and it will be 0 otherwise. 0 here, 0 here. Yeah. And now if we observe, I have overlap here and here, here and here, here and here, and there is no overlap after that and no overlap before this. So this is for n equal to 4, which means that y of 4 is equal to 1 into 1 plus 1 into 1 plus 1 into 1, which is equal to 3. Okay, now again I shift it by 1 unit towards right. So what I have is something like this. And it will be 0 everywhere else. So this is basically x of k 5 minus k, which means that n is equal to 5. And now if you observe carefully, I have an overlap here and here, here and here, and there is no other overlap. So what I have is y of 5 is equal to 1 into 1 plus 1 into 1, which is equal to 2. Now again I'll shift it by 1 unit towards right, which is something like this. Okay, and there is 0 everywhere else. So this is basically x of 6 minus k, which means that n is equal to 5. N equal to 6 means y of 6 is equal to, there is only one overlap, that is at 3, here and here. So we have 1 into 1, which is equal to 1. And now if I shift it further, then there won't be any overlap, and that's why after n equal to 6 it all will be all 0. Similarly, before n equal to 0 it will all be y of n will all be 0. So therefore this yn is basically a sequence which looks like 1 2 3 4 3 2 1, which starts at at this location, that is at n equal to 0 it is 1. So this is starting here, so it is 1 2 3 4 till 4 it goes, and then it reduces to 3 2 and then back to 1. So this is y of n that we are having. Okay. Now so let us try to sketch this plot. So let's say this is n, this is yn, okay, and this is 0, this is 1 2 3 and this is 1 2 3 4 5 6 7 8 and so on. So at n and it goes max to 4, so this is 1 2 3 and 4. So basically at 0 it is 1, then it raises to 2, then it rises till to 3, then it goes to 4 at 3, then again back to 3 2 and 1, and then it is 0 everywhere else. Similarly in negative side it is 0. So this is the y of n. So this is basically my yn, which is nothing but my convolution of xn with itself, that is xn. So this is the completion of the step 1 part. Now what do we have is step 2, and that is finding y1 of n. Okay, so now what we need to do is we need to find what is the value of y1 of n. Now observe that y1 of n, so y1 of n is basically repeated version of yn after every 10th sample. Okay, so let us try to sketch it. Okay, so this is my n axis, this is yn or y1 of n. This is 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 and so on. Then here it goes to 1 2 3 4. Let me draw some reference lines as well so that it's easy to mark them. 1 2, this is for 3, and for 4. Yeah, okay. So basically at 0 it is 1, 2, 3, 4, then it goes back to 3, 2 and 1, then it is 0 and it starts repeating at 10. So it is 10, then it goes to 2, 3, 4, 3, 2, 1, 0, 0, 0, then again it repeats from 20, that it takes the value of 1 at 20, then 2, 3, 3, 4, 3, 2, 1, then again 0, and then at 30 it takes the value as 1, at 31 2, and so on. Okay, so this is basically how the signal y1 of n looks. And if you observe carefully, this y1 of n is periodic with period 10, which means that its angular frequency omega naught is 2 pi by n naught, which is equal to 2 pi by 10, which is equal to pi by 5. And now we need to find what are the Fourier series coefficients of this signal. So for that I'll just copy this signal onto the next page. Okay, so this is y of n that we are having. Okay, yeah, and now we'll do the step 3. And what we know is this n naught is equal to 10 and omega naught is equal to pi by 5. This we have obtained. And now what we need to find is, we need to find Fourier series coefficients. That is Ck. Okay. Now this Ck is basically 1 by n naught, that is 1 by 10 summation k n running from 0 to 9 xn into e power minus j k omega naught is pi by 5 into n. So this is the value of Ck. Okay, so now this I can write as 1 by 10 inside the bracket x1 x0 plus x1 into e power minus jk pi by 5 plus x2 into e power minus jk 2 pi by 5 plus x3 into e power minus jk 3 pi by 5 plus x4 into e power minus jk 4 pi by 5 plus x5 into e power minus jk 5 pi by 5 plus x6 into e power minus jk 6 pi by 5, and remaining from 7 to 9, x7 to x9, it is all 0, so I can simply ignore it. So once we have this, let us substitute back the values. So it is 1 by 10, x0 is 1 plus 2 into e power minus jk pi by 5 plus 3 into e power minus jk 2 pi by 5 plus 4 into e power minus jk 3 pi by 5 plus 3 into e power minus jk 4 pi by 5 plus 2 into e power minus jk 5 pi by 5 plus 1 into e power minus jk 6 pi by 5. Okay, so this is what we are having right now, and let's try to simplify this further. Okay. So this is what we are having. So this is my CK. So now this what I'll do is I'll take the coefficient of this term of 4, that is this complex exponential associated with this 4 outside, to make some manipulations. So what I'll do is I'll take this e power minus jk 3 pi by 5 outside upon 10 inside the bracket. What I have is 1 plus 2 into e power minus jk 2 pi by 5 plus 3 times e power minus jk pi by 5 plus 4 plus 3 into e power jk, I'm sorry, it's plus here, minus jk pi by 5 plus 2 times e power minus jk 2 pi by 5 I'm sorry, here we'll have e power, shift it, yeah, e power jk 3 pi by 5 and plus e power minus jk 3 pi by 5. So now what I'll do, I'll combine the terms which are having same integer coefficients. Okay, so what I'll do is, so let me write this as e power minus jk 3 pi by 5 upon 10, and I'll write this 10 as 2 into 5, so I'll keep this 5 inside and shift the 2 inside. So what I have is these two terms, this one and this one. So this is basically equal to e power j k 3 pi by 5 plus e power minus j k 3 pi by 5 by 2 plus I have these terms which is corresponding to 2 plus 2 into e power j k 2 pi by 5 plus e power minus j k 2 pi by 5 upon 2. Then I have the terms corresponding to this 3. So plus 3 into e power jk pi by 5 plus e power minus jk pi by 5 whole divided by 2 plus 2, which is 4 divided by 2, which is equal to 2. Now if you observe carefully, this red term, this term here is basically equal to cos of 3 pi by 5 k. This green term is basically cos of 2 pi by 5k, and this purple term is basically cos of pi by 5k. So what I'll do, I'll just replace those terms. So for that, let's write it as e power jk 3 pi by 5 upon 5 inside the bracket. This red term is basically cos of 3 pi by 5k plus 2 times cos of 2 pi by 5k plus 3 times cos of pi by 5k plus 2. Therefore, what we have is ck is equal to 1 by 5 into e power minus jk 3 pi by 5 inside the bracket. We have 2 plus 3 times cos of pi by 5k plus 2 times cos of 2 pi by 5k plus cos of 3 pi by 5k. And now if I find out the DC coefficients, that coefficient, that is C0, then it comes out to be 1 by 5 as it is into 1 inside the bracket, 2 plus 3 plus 2 plus 1. So this is basically equal to 2 plus 3 5, 5 plus 2 7 plus 1 8. So this comes out to be 8 by 5. So this is the Fourier series coefficients of 1 by y1 of n, which is basically repeated version of this yn, which is obtained something like this with a period of 10, and this yn is basically convolution of xn with itself. I hope this is clear to everyone. So if you have any questions or any doubts, please feel free to ask. If not, you may leave the meet. Thank you so much. Thank you.